Welcome back to our course in stochastic processes. We are in the middle of our chapter on Markov processes, and today we will treat the special case of time homogeneous Markov processes. That's a bit special because there we are encountering some algebraic structures actually, which are semigroups, which also have generators of semigroups. So let's see what it is. So the title is here really semigroups and their generators. But first, let's see what we mean by a time homogeneous Markov process. So we always had these Markov kernels, mu st, and the operators tst. And if they depend on s and t only by their time difference, we say that the Markov process is time homogeneous, because it only matters how much time passes from s to t and not what time it actually is, s for example. In this case, we will call the t the operator semigroup and the mu the transition semigroup. And why is that a semigroup? So what is a semigroup actually? So in a semigroup, we can define a plus, basically. And the semigroup property is this here, mu s, mu t is mu s plus t. So recall mu s, mu t, that's the transition kernel from time 0, say, to time s, which we integrate out, further to time t. And essentially what happens? Well, time s plus t passes, so that's exactly what is true. Mu s, mu t is mu s plus t, and that's the semigroup property of the transition semigroup. And for the operator semigroup, it's the same. Ts, tt is ts plus t. And these two things are actually connected to the Chapman-Kolmogorov equations. So that were these here. And these for the Markov transition semigroups and operator semigroups, or operate Markov kernels and transition operators. And when you plug in a mu which only depends on the time difference, then you get exactly what is written here. In addition, the distribution of the Markov process, which is defined by the finite dimensional distributions, is given by this here, which is again a special case of what we had last time here, where we have just plugged in a mu which only depends on the time difference. So here we are. Well, the strong Markov property is in this case also can be formulated more easily just by plugging in a random time here and here into the Markov kernels and the transition operators. But we will not need the strong Markov property today. And then let's consider something else. So let's not think about a Markov process at the moment. That's further down here on the slide. But let's think of an operator semigroup. So assume we have this family of operators. We just have this here, so they map functions to functions. And they have the semigroup property, so tt, ts is t plus s. Such operators can have properties. For example, they can be positive. So if f is non-negative, then ttf is non-negative, then tt is called positive. It's a contraction. So if whenever f is between 0 and 1, then ttf is also between 0 and 1. It's conservative if tt1 is 1. It's strongly continuous if TTF minus F, so the difference between TTF and F, for small t vanishes. For many F's, and the F's we are taking here are the continuous and bounded ones. And it's called a Feller semigroup. If TTF converges to F, similar to this here, and TTF is continuous for all F. Yeah. So that's a Feller semigroup. And we call a Markov process Feller process if the operator semigroup is a Feller semigroup. Okay, that's just notation. But the more interesting things is when we have a Markov process, a time homogeneous one, it has an operator semigroup, TT. And which properties does this semigroup here have? So recall T F of x is the expectation of f of xt when we start in small x. And of course, if f is not negative, then this expectation here is also non-negative, which means that this tt here is positive. Is it a contraction? Yes, it's a contraction because if f is less than or equal than 1, the expectation is also less than or equal to 1, which makes it a contraction. Is it conservative? Well, if f is 1, the expectation of 1 is 1 because we're integrating with respect to a probability measure, which means that this operator semigroup is conservative. And this is written on the next slides here. Conservative, positive contraction. That's what I just explained. What else? So, Feller processes are somewhat nice. So we can make up our minds what Feller processes are, what it means for a process to be Feller. So for example, we had this thing here, TTF converges to F as t goes to infinity. And in probabilistic terms, that means that xt converges, well, in probability to x0 if t goes to 0. So why is that? So let's try to prove that really quick. So there are two directions here, from left to right. And let's do a usual trick. G of y equals the distance between x and y minimum 1. So that's a bounded and continuous function for fixed x. And we have the expectation when we start an x of this function. So of r x0 xt minimum 1. This is exactly the Feller's the semigroup TTG of small x of x0, because we start in x0. And as t goes to 0, we are in the direction from left to right. We know that this here converges to g of x0, which is 0. TTG of x0. Yeah, so x0 equals x. When you start like this here. Okay. That's from left to right and from right to left. That's even simpler, I guess. So we have that xt converges not only in probability but also weakly. So for bounded and continuous f, we have that TTF of x is the expectation when we start an f of xt, but xt converges to x0, so this here, as t goes to 0, converges to expectation f of x0, which is f of x because x0 equals x. And that's the reason for this convergence here. So recall here. The other bit here, TTF, is also continuous. And I didn't really find a good probabilistic explanation for this thing here. So TTF is continuous. We have to check by ourselves in specific examples. For example, Poisson point process and Brownian motion are Feller processes. In both cases, we can define the increment between time 0 and time t. Then we know that zt is Poisson lambda t distributed, or n0 t distributed for Brownian motion. We can write that TTF, that's the expectation of, well, f of xt when we start in x, but xt is x plus zt. In both cases, we have that zt converges to 0 when t goes to 0, because this here becomes a Poisson distribution with parameter 0, and there's a weak convergence of Poisson distributions when the parameters converge. And the same here for the normal distribution, so that converges to 0 in both cases, which means TTF converges to f of x. And that's already it for the first thing. And the other thing is, we also had that already, the map which maps x to TTF of x. If f is continuous, that's a continuous function where you need dominated convergence and continuity of f in the proof when you want to write it out. And therefore, this is also a continuous function. And these two properties mean that the Poisson point process and Brownian motion are Feller processes. Okay. It was promised that we have semigroups, and semigroups have generators. So what's this? The generator is again an operator, meaning it maps functions to functions. And which function is gf? That's the function which maps x to this limit here. So, and you realize quickly that this is very similar to a time derivative. The only thing which is special is that in the numerator you have an expectation. So you have an expected derivative, so to speak. And you commute f of xt minus f of x, so that's the increment, what f of x does between time 0 and time t. But only the expected one, and you divide it by t, and let t go to 0. You can also write it in terms of the operator semigroup. The set of functions f for which this here exists is called the domain of G. Okay. So that will be very helpful because maybe we're not so happy only dealing with the TT here, the operator semigroup. We want to have also this generator here, and we will see where that is really a nice thing to study and very helpful. But first, let us just compute something, which is the generator of the Poisson point process and the generator of Brownian motion. Because these are very specific things. And we will have more examples in the next video also. So if X is a Poisson point process with rate lambda, what is the generator? First, this is here true by definition, because if Pt is the Poisson point process at time lambda, it's distributed like X plus Pt, where Pt is here the Poisson distribution with rate lambda t, actually, like this. Well, when we integrate out this expectation here, we get a sum. If Pt is 0, this here vanishes. But if it's 1 or above, the probability distribution of Pt is either minus lambda t to the power of k divided by k factorial. That's the probability that this here is k. And then you have fx plus k minus f of x. We divide by t, by the definition of the generator. And now we have to be careful because, well, so t is going to be small. So this t is going to be small here. So there's a linear term where we have lambda t to the power of 1. Let's look at this here. Lambda t to the power of 1 divided by t, there are lambda stays. We also have 1 minus e to the lambda t. So for small t, that's very close to 1. So we can assume it's going to be 1. Because t at least occurs here at a linear, with a linear term, and all higher order terms vanish actually, because I divide by t, so something above an exponent above 1 stays, and t goes to 0, so that one will go. So the only thing stays here in this formula here is the linear term for t equals 1. This here is going to vanish. Lambda t divided by, well, k is 1. I have an f of k, x plus 1 minus f of x here. And what stays is lambda times f of x plus 1 minus f of x, and this is exactly what I've written here. So that was for the Poisson point process. And maybe the structure of this formula is the following. Here's the rate. Okay, then here's the function of the new state minus function at the old state. And we will see that this pattern is more general than just for the Poisson point process when we are dealing with jump processes. But when we are dealing with something like Brownian motion, which is continuous, it's a bit different. But here still we can compute things, because we know again how the increment is distributed. We can, so at small times t, if we have z equals is an n01 random variable, we have that square root of t times z is the distribution of the increment between time 0 and time t. So we can write the generator as this limit here. And t is small. And since t is small, we can try to do a Taylor approximation here. So the Taylor approximation starts with f of x, but we subtract that. We have f prime of x times the increment, that's this thing here. We have 1/2 f double prime times the square root of this, so t times z square. And there's a remainder from the Taylor expansion, where you have some y here, which is between 0 and z. Or z square, yeah. And first of all, well, I have the expectation here. The expectation of z is 0. That vanishes. So this term goes. The second term is easy because we have a z square here. The expectation of z square is 1. And this is here about to stay 1/2 f double prime of x. So that one is okay. And for the remainder has here a t, which goes away. Expectation of z square is 1. Okay, that's not so hard. And then we have f double prime of x plus something minus f double prime of x. But since f here is assumed to be twice continuously differentiable with continuous derivatives, this thing here goes to 0 because y is very close to z square, and that goes to 0. And yeah, so sorry, not z is going to 0, but t times z square is going to 0. Okay, for this reason, we've now computed the generator of Brownian motion, which is 1/2 f double prime, which will also play a big role later. Okay, so what can we do with these generators? We can write down stuff. For example, I will compute here this equation. So f is a function and gf is also a function. And when you look at this equation here closely, so this here is a function at time t. That's the function initially. And I'm adding the integral. So this here should be something like the time derivative of this function by the usual theorem of integration and differentiation. And so, well, this here should be the differential of this here. And it is actually, because it's a generator, and that's exactly here the form yg can be assumed to be a time derivative also. So let's see how that occurs and what the lemma here tells us. We assume I have a generator, I have a domain, and well, I have a d here such that g of all functions of the domain are continuous, so as in the Feller semigroup. Then, if I'm starting out with a continuous function, then I have the following, that I can apply g to the integral over ts. And the result is t at the final time minus f at the beginning. And then the questions here, okay, g, because it's a derivative, it's a linear operator. And I have g here of an integral. An integral is basically a sum, and a linear function of a sum is the sum of the linear functions. And so it's possible to write g inside here the integral. And even more is possible. So gts, that's not how I write it, I write tsg. So remember, f is a function, gf is also a function, and since gf is a function, I can apply ts to this function and evaluate the whole thing at x. Exactly. So how can this be proved? So first equation, which is this one here, I guess. Yes. So let's start at the right-hand side. I apply g here to this thing. And applying g means I compute 1 over time expectation of, well, expectation of, well, this thing here at time h minus this thing here at time 0. So I have the expectation integral from 0 to t, tsf of xh minus tsf of x ds. Well, here time h passes, here time s passes, so in total time s plus h passes. So I can also write it like 1 over h expectation integral from 0 to t, ts plus h f of x minus tsf of h ds. And when you look at this here, the integral here is almost over the same set. So, but here I'm integrating s plus h, and here I'm integrating s. So what happens if this here is from 0 to t? I'm integrating from h to t plus h, and I'm subtracting the thing from 0 to t. So I'm basically adding and subtracting all the areas where I have a green and a yellow line here, and I remain with this thing positive and this thing negative. So I have 1 over h. So positive is t until t plus h, tsf of x ds, and I subtract integral from 0 to h, tsf of x dx. And now h goes to 0, so I have a very small integral here, but the width is h and divide by h. So the first term converges to tf of x. Well, in the second term, s is very close to 0, so that one converges to t0 f of x, which is f of x. And that's exactly what was written here. So I've shown the first equation. Then for the other statements, so here I show that I can exchange this g and this tf here, and that I have this equality of expectations. For example, I can compute the time derivative of exf of xt. By definition of the time derivative, limit h goes to 0, 1 over h, expectation when starting in h, f of xt plus h minus f of xt. Well, this here I can write as ttf at xh, and the other term as ttf. But by all this linearity and boundedness, I want to write it as tt, then limit h goes to 0, and then 1 over h expectation f of x h. Well, minus f of x, like this. Now I can pull in the tt again. The 1 over h and the expectation f of TTF of xh minus TTF of x. Well, and TTF is a function, and this here is then the generator applied to TTF, and all this applied to x. And therefore, we can write that TTF of x minus f of x, I can write it as the integral of the derivative d by ds expectation f of xs ds. But this time derivative we just computed as this generator here. Yeah. And I forgot something. Here. So what happened here? So here I computed that this limit here is GTTF. I could also have done it differently because, let me write it in green, this thing here, that is by definition GF of x. This limit here. Which means that, okay, computed here, that's GTTF, but it's also TTGF of x, like this. As a result. So G and TT, they commute. And when you have this here, I can now either use this or this. And when I use the second, that's then also the second equality, T. So this time derivative is then TSGF of x ds. And this is exactly the second equality here. Well, and for the third one, I mean, by definition here, this is TTF of x. And what's this here? This is TSGF of small x. And since TSGF of x, I can exchange G and T. And well, this is the same as this difference here. And so this here must be TSGFX. That's exactly what's written down here, right? So this is only the probabilistic expression for the last equation here. And we're done with this here. And I have two more slides actually. First of all, I claim, well, this domain. The domain was the set of functions where the generator can be defined for a strongly continuous semigroup. And then the domain is dense in the set of all bounded continuous function, which is sometimes useful. And the reason is, if I have any bounded continuous function, okay, this here is pretty clear. Because I have a Feller semigroup, I know that TSF converges to F as S goes to 0. And yeah, that's also continuous in S, so this converges here to F. And these functions here on the left-hand side, they must be in the domain of the generator. Because, as we just showed, you can use this here. The integral over 0 from t over TSF, which is exactly what I need here. So I can compute the generator of the left-hand side. And that means that the domain is dense because we started out with some bounded continuous function and we approximated it by functions in the domain. Okay, that was this. And the second one, that's really important also. We can derive martingales from Markov processes, from time homogeneous Markov processes. And let me focus on the first martingale here, on this one. I'm claiming when I have a Feller semigroup with some generator G, and GF should also be bounded continuous, then f of xt minus the integral over the generator of xs is a martingale. So in order to prove this, we take s less or equal than t, and we can compute the increment. That is f of xt minus f of xs. Sorry. F of xs minus the integral from 0 to t over the generator, and f of xr dr. Conditional on fs. So when I compute this, I'm computing the increment between time s and time t. And I condition this on fs, and if this is 0, then I know that this process here must be a martingale. First of all, conditioning on fs or on xs is the same because we have a Markov process. So I have f of xt minus f of xs minus the integral from 0 to t gf of xr dr, conditioning on xs. And then, well, I started in xs, and the time which passes until xt, time t, is t minus s. So this here is t minus s f of x. F of xs, sorry. F of xs, because it starts in xs, minus f of xs. Minus the integral from s to t. And here again I have a conditional expectation. I'm conditioning on xs, and I have t r minus s gf of x dr. And when you look at this, that sounds familiar. It's very similar to this thing here. I have, okay, xs is, sorry, I needed also an xs here. But then it's really the same as in the other slide. The only thing is I have here t minus s where I had t before, and we computed that this is the same as this here, which means that the whole thing here equals 0. And we have shown that this here is a martingale. And there are more martingales for Markov processes. For example, this thing here, as long as f is nice. That's also a martingale, which might be useful also later. Okay, that was it for operators, semigroups, and their generators. And next time we will deal with some examples. See you then.